Euler's method is simply an estimation formula to find a point close to its original. With an initial point of a comma b and a provided delta x, which is how far you'll be moving each time you use the formula, you're able to find a point close enough to the original that you're able to use. Now, when you're given an equation, you'll have an initial point, a delta x, which is how far you will be moving, which for this one we'll use 0.1, and an f prime equation, which could be as simple as xy, which we'll be using in the next example. Now, this works because with your initial point, you'll be using y old, which is b in this example. Then you'll add that to f prime of old. So you'll use both a and b, which are your initial points, to plug into this equation to get an answer, which would be a times b. And your delta x is provided, which is 0.1. That will provide a tangent line and a point right there. Now your new x value will be 0.1 larger, and your y value will be given by this equation. To find the next step, since that's our goal, you do this equation again, but with your new values here to find another value. That gives you another tangent line and a point, fairly close to what you're looking for. Now, even though these 2 points are not the same, this is so zoomed in and so close that it practically makes no difference. To start off, we're going to be creating a slope field with dy dx equals x times y. The slope field will represent the slope at which the points are at the given x and y coordinates. Starting with 1, 1, you have an x value of 1 and a y value of 1. So you can plug these in, which will be into this equation, and you will get x times y equals 1. You'll create a slope of 1 at that point. Going on to 1, 2, with an x value of 1 and a value of 2 for y, 1 times 2 equals 2. And then you'll draw on a slope of approximately 2. These don't have to be exact because it'll be difficult further down the road. With 1, negative 1, you will get negative 1 as an answer. The slope will go the other direction. 2, 1, when you plug those in, will give you a slope of 2. And then here you have x value of 2 and a y value of 2. That'll give you a slope of 4. 2, negative 1 will give you a slope of negative 2, which will be slightly steeper. And then over here, we have negative 1, 1, giving you a slope of negative 1. Then we have negative 1, negative 1, and you will have a slope of 1 because you'll be multiplying them together. Lastly, you have negative 1 times 2, which gives you a dy dx of negative 2. This is how you create a slope field to start off, and this provides you the slopes of the points of any equation at a certain point.
Now we'll find the particular solution to this differential equation, starting with the initial condition 1, 1. So, first off, we need to separate the variables, getting the x's by each other and the y's by each other. We will do this by dividing through by y, getting dy over y, and then we will multiply through by dx to get x dx. Then we will integrate both sides, so getting the integral of dy over y equaling the integral of x dx. We will take the integrals and we get ln of y equals x squared over 2 plus c. Then we will e to the both sides, getting y, because the e to the ln of y is just y. So we will get y equals c e to the x squared over 2. We can bring the c out in front, because if you were to just do this as e to the x squared over 2 plus c, that can also be written as e to the x squared over 2 times e to the c. This here is just a constant, so we can multiply it by everything here, giving us c e to the x squared over 2. Now we will use our initial condition and plug it in for x and y in this to find what c is equal to. So 1 equals c e to the 1 squared over 2. 1 equals c e to the 1/2. So then we find e to the 1/2. So e to the 1, e to the 1 over 2. And so we get 1 equals 1.649 c. We will divide the constants. So 1 divided by 1.649 equals, giving you c equals 0.606. Now we'll plug this back into the equation here, and we will get a final answer of y equals 0.606 e to the x squared over 2. Using the concept you viewed earlier, we're going to now apply Euler's method to the equation we've been using before. We're going to estimate x equals 1.5 starting at the point 1, 1 with 2 steps of 0.25. So first, we'll take the y old value, which is 1. So we'll put 1 plus f prime, so dy dx, at this point, which will be just 1. And then we'll multiply it by our delta x value of 0.25. So that'll give us out 1 plus 1 times 0.25, which will give us 1.25. So now we have a new point, 1.25, comma 1.25, and we're going to use this now to estimate 1.5. So the y new is equal to our old y value, so 1.25, plus f prime of this point, so that will equal 1.25 times 1.25, which equals 1.5625. Then we will multiply this again by our delta x value. So this will come out to 1.25 plus this value before times delta x, which gives us 1.641.
We'll be going through one more example, but this time dy dx equals x squared divided by y. I've already placed the points here, so starting off we have 1, 1. That'll be 1 squared divided by 1, which still equals 1. 1, 2 will be 1 squared divided by 2, which equals 1/2. Then 1 squared divided by -1 is -1. Following with 2 squared divided by 1, this will be 4. 2 squared, which is 4, divided by 2 will equal 2. And then 2 squared divided by -1 equals -4. -1 squared is still 1, divided by 1 gives you 1. And then 1 squared divided by 2 is 1/2. And -1 squared divided by -1 is -1. This is your slope field for the following differential equation.
Now we'll find the particular solution for this differential equation using the initial condition 0, 1. So first, we need to separate our variables again, getting y and dy together, and dx and x squared together. So we'll multiply through by y, getting y dy equals, multiplying through the dx, x squared dx. Now we have to integrate both sides, getting y dy equaling the integral of x squared dx. These will equal y squared over 2 equals x cubed over 3 plus c. Now, we need to multiply both sides through by the 2, getting y squared equals x cubed, or 2x cubed, I'm sorry, over 3 plus c. The c stays as a c because a constant times 2, with us not knowing what the constant is still a constant. So it stays as the c. Now we're going to take the square root of both sides, getting y by itself and it being just y. So we'll get square root of all of that, so 2x cubed over 3 plus c. And we're going to plug in our initial condition to find what c is. So 1 equals the square root of 2 times 0 cubed over 3, which will turn out to be 0, plus c. So rad c is equal to 1. Squaring both sides, we get c equals 1. So our final equation will be y equals the square root of 2x cubed over 3 plus 1. Now we will use Euler's method with our differential equation to estimate 0.6 with a step size of 0.2 using 3 steps of this. So our y old value starting at 0, 1 is 1, plus the f prime value at that point, so 0 squared divided by 1 will just equal 0, so we'll get 0 times 0.2, which will turn out to be 0, so we'll get the new y value is going to equal 1. So our new point is 0.2, 1. So we'll go through a second step of Euler's method. So the new y value will equal 1 plus, so 0.2 squared equals 0.04 times 0.2, and when you add those together, you'll get 1.008. So our new point now is 0.4, 1.008. So the y new value here is what we're going to find with our third step. So 1.008 plus the value of this our new point in the differential equation. So we'll get 0.4 squared divided by 1.008. So now we have a value of 0.158 times 0.2, which that all comes out to equal 1.008 plus 0.158 times 0.2, that will equal 1.039. So we get the final point of x equals 0.6, 1.039.